Hello there. Welcome to this quiet space, a sanctuary for your mind and a resting place for your body. I am so glad you have joined me tonight. Before we begin our ascent into the stars, take a moment to acknowledge the space you are in. Feel the mattress beneath you, supporting your weight completely. Feel the air in the room, cool and still against your skin. You have no responsibilities now, no problems to solve, no clocks to watch. Your only task is to listen to the sound of my voice and let your imagination drift upward, beyond the roof, beyond the clouds, and into the velvet embrace of the night. Tonight, we begin a three-part journey. We are going to explore our home, the Milky Way Galaxy, in a way few ever do. We aren't just looking at a map. We are feeling the rhythm of its motion and the depth of its history. In this first hour, we will linger in the outskirts. We will visit the ancient suburbs of our galaxy and the invisible forces that hold the stars in place. Take a deep breath in, hold it for a moment, and let it out slowly. Imagine that with every exhale, you are growing lighter. You are becoming as weightless as a photon, drifting away from the lights of the city, rising through the atmosphere until the blue of the sky fades into the perfect, deep black of the vacuum. We find ourselves now in the galactic halo. This is the great, spherical envelope that surrounds the flat disk of the Milky Way. It is a place of profound silence and immense scale. If the disk of the galaxy is a bustling city, the halo is the high, lonely mountain range that surrounds it. Here, the stars are not packed together in crowded arms. They are solitary travelers, spaced so far apart that they may never see another sun as a bright neighbor. These stars are the elders. Scientists call them metal-poor stars because they are made almost entirely of hydrogen and helium, the original elements created in the Big Bang. They contain very little of the iron, carbon, or gold that make up worlds like ours. They are fossils of the early universe, shining with a steady, ancient light. As you drift among them, feel the age of these suns. They have been orbiting the center of our galaxy for over 13 billion years. They have watched the Milky Way assemble itself from the wreckage of smaller worlds. Notice how these stars move. They do not follow the neat, circular paths of the stars in the disk. Instead, they move in long, plunging orbits, diving down through the galactic plane and soaring back up into the dark. They are like quiet guardians, watching over the spiral from above and below. Let your mind follow the path of one of these ancient stars. It is a slow, patient journey that takes hundreds of millions of years to complete. There is no hurry. There is only the steady, rhythmic pull of gravity. Within this halo, we come across the globular clusters. Imagine a sphere of light, so dense and so bright that it looks like a pile of diamonds on black velvet. Each of these clusters contains hundreds of thousands of stars, all bound together by their mutual gravity. They are among the oldest structures in existence. Inside a globular cluster, the stars are so close that the night sky on a hypothetical planet would be as bright as day. Pause here for a moment. Imagine standing in the heart of a globular cluster. Everywhere you look, there are suns, red giants, white dwarfs, and ancient yellow stars, all humming with the energy of billions of years. These clusters are the anchors of the halo. There are over 150 of them surrounding our galaxy, like a crown of jewels. They are survivors of a younger, more violent universe, holding their shape against the tides of time. As we drift further into the halo, we must acknowledge the great mystery. The stars and the clusters we see are only a tiny fraction of what is actually here. By all the laws of physics we understand, our galaxy should fly apart. The stars at the edges are spinning too fast for the visible mass to hold them. The reason they stay is because of the dark matter halo. This is the invisible scaffolding of our home. It does not reflect light. It does not emit heat. It is a substance we cannot see or touch, and yet it is the most abundant thing in the galaxy. It surrounds us in a massive, heavy sphere, providing the gravitational glue that keeps the spiral arms from shattering. Imagine a vast, unseen ocean, and the stars are just the phosphorescent foam on the surface. We are floating in this dark, silent sea. It is a comforting thought that even in the emptiness of space, there is something holding everything together. something vast and steady that ensures the stars keep their place. Before we end this first stage of our journey, look closely at the ghost streams. These are ribbons of stars that wrap around the Milky Way like silver threads. They are the remains of small dwarf galaxies that wandered too close to our home billions of years ago. The Milky Way's gravity reached out and gently unraveled them, stretching them into long, thin trails. The Sagittarius stream is one of these. It is a river of stars that circles the galaxy, a memory of a collision that happened eons ago. We are living in a galaxy that is a beautiful mosaic built from the ruins of others. It is a story of integration and growth. Nothing is ever truly lost in the cosmos. It is simply reshaped, reborn into a new form, and added to the grand design. Feel yourself drifting now, high above the turning spiral. You are safe in the halo. You are cradled by the dark matter and watched over by the ancient stars. The disk of the galaxy lies below you, a glowing whirlpool of potential, waiting for us to descend into its arms in the next hour. But for now, stay here in the quiet. Let the scale of the halo remind you of how small and how peaceful your worries truly are. You are a part of this ancient, invisible structure. You are a traveler in the deep. Rest now. The journey continues in the silence. The stars are turning. The galaxy is breathing. Sleep. We are still drifting in the high, thin reaches of the galactic halo, but the view is beginning to change. Below us, the hazy, ethereal glow of the disk is becoming more defined. It looks like a vast, glowing whirlpool made of cream and silver, spinning so slowly that to our eyes, it appears perfectly still. But we know better. We know that everything down there is in a state of constant rhythmic motion. Every star, every cloud of gas, every grain of cosmic dust is dancing to the tune of gravity. Before we descend, let us linger here at the threshold. The transition from the halo to the disk is not a sharp line. It is a gradual thickening of the light. Imagine you are standing on a high mountain peak at twilight, looking down at a distant, fog-filled valley. The halo stars are like the rare, lonely lights of a mountain cabin, while the disk is the sprawling, interconnected glow of a great metropolis. Look to your left. There is a red giant star drifting solo in this region. It is massive, hundreds of times the size of our own sun, but its light is cool and amber. This star is an elder, nearing the end of its long life. As we drift past it, imagine the immense scale of its surface. It is not a solid thing, but a boiling, churning sea of plasma. Great loops of magnetism rise from its surface, arching thousands of miles into the void before crashing back down. Because the gravity here in the halo is so weak, the star's outer atmosphere is puffed out, translucent and ghostly. It is a quiet, glowing monument to the passage of eons. This star is a storyteller. In its outer layers, it carries the history of the early Milky Way. Because it has lived so long, it has seen the galaxy grow through cannibalism. It was there when the Sagittarius dwarf galaxy was first captured by our gravity. It watched as that smaller world was stretched and torn, its stars becoming the silver threads of the stellar streams we saw earlier. The Milky Way is not a finished object. It is a work in progress, a gravitational structure that is deepening and thickening over time. Even now, as you lie there, breathing slowly and deeply, the galaxy is pulling in fresh material from the intergalactic medium. It is breathing in hydrogen gas, the raw fuel of the universe, and drawing it down into the disk where it will eventually become new stars, new planets, and perhaps, one day, new life. As we begin our long, slow descent toward the disk, feel the density of the universe begin to rise. The silence of the halo is being replaced by a subtle, magnetic hum. We are entering the thick disk. This is a region of older stars that orbit the center with a bit more chaos than the stars in the thin, bright spiral arms. These stars are like the older generation of a family, settled and steady, providing the structural foundation for the younger, more vibrant stars below. Notice the colors shifting. In the halo, the light was mostly golden and red, the colors of age. As we sink lower, we begin to see the first sparks of blue. These are the blue stragglers, stars that seem younger than they should be. They have stayed young by colliding with other stars or siphoning gas from a companion, a cosmic fountain of youth. They remind us that in the vastness of the galaxy, there are always exceptions to the rules, always moments of unexpected energy. We are now passing through a cloud of diffuse, ionized gas. It is so thin that it would be a better vacuum than anything we can create on Earth, yet it glows with a faint purple hue. This is the interstellar medium, the air of the galaxy. It is filled with the ghosts of dead stars. When a massive star explodes as a supernova, it flings its heart out into space. Oxygen, nitrogen, iron, and gold. That material drifts here, in these quiet, cold spaces, waiting for gravity to find it again. Think about the iron in your own blood. It was forged in the white-hot core of a star just like the ones we are passing. It was cast out into the dark, spent millions of years drifting in this purple haze, and was eventually swept up into the cloud that formed our Earth. You are not just looking at the galaxy, you are looking at your own ancestors. You are made of the very dust that is currently shimmering outside your window in the deep of space. The descent is slow, like a feather falling through a still room. We are approaching the thin disk, the place where the spiral arms reside. This is where the story of the sun begins. This is where the density of gas and dust becomes high enough to form stellar nurseries. Imagine a great curtain of dark, cold dust rising up to meet us. To the naked eye, it looks like a void, a hole in the stars. But we have infrared eyes tonight. We can see through the dust. Inside these dark clouds, thousands of protostars are beginning to glow. They are not yet stars. They are giant balls of gas, shrinking under their own weight, getting hotter and hotter. As we drift further from the local bubble surrounding our sun, the structure of the Milky Way begins to reveal its true colossal scale. We are now entering the Perseus Arm, one of the two major spiral arms of our galaxy. If the Orion Spur was a quiet side street, the Perseus Arm is a bustling celestial interstate. It is a massive, curving river of gas, dust, and millions upon millions of stars, all caught in a high-density wave that ripples through the disk. As you breathe in deeply, imagine the sheer density of this place. The stars here are packed much closer together than in our neighborhood. The sky, if you were standing on a planet here, would be a riot of color, dominated by massive, brilliant blue stars that burn with a fierce, short-lived intensity. These are the O and B type stars, the giants of the cosmos. They are born in the heart of the spiral arms, where the density waves compress vast clouds of hydrogen gas until they ignite. But these blue giants are tragic figures in our story. Because they burn so brightly, they exhaust their nuclear fuel in just a few million years, a mere blink of an eye in galactic time. They never live long enough to drift out of the spiral arms where they were born. They are the streetlights of the galaxy, illuminating the curves of the spiral for a brief moment before vanishing in spectacular supernova explosions. Feel the vibrations of these distant explosions in the silence of your mind. When one of these giants dies, it doesn't just disappear. It collapses under its own weight and then rebounds in a blast that can outshine the entire galaxy for weeks. This shockwave tears through the surrounding space, acting like a cosmic snowplow. It slams into nearby clouds of cold gas, squeezing them together and triggering the birth of 1,000 more stars. In the Perseus Arm, life and death are intertwined in a frantic, beautiful cycle of renewal. As we drift across the gap between the Perseus Arm and the Sagittarius Arm, we enter the voids. These are not truly empty spaces, but regions where the star density drops significantly. The light becomes softer, more diffuse. This is the realm of the interstellar medium in its most tranquil form. Imagine a fog made of microscopic diamonds, graphite, and silicates. This is the cosmic dust. It is so fine that it feels like nothing, yet it has the power to blot out the light of billions of stars. As we move through this dust, the light from the galactic center turns a deep, sunset red. The dust scatters the blue light and lets only the long, red wavelengths pass through. It is a permanent twilight, a quiet moment of reflection before we reach the next great structure. Floating in this gap, we find the rogue planets. These are lonely worlds that have no sun, Perhaps they were once part of a solar system but were flung out into the dark by a gravitational tug-of-war between larger planets. They drift through the interstellar voids in total darkness, frozen and silent. Think of the peace on such a world. No seasons, no days, no nights. Just the eternal, unchanging view of the Milky Way arching overhead. Some of these planets might have hidden oceans beneath shells of ice, kept warm by the radioactive decay of their own cores. In the vast, dark stretches of our galaxy, life might be huddling in places we never dared to imagine. We are now approaching the Sagittarius Arm. This arm is famous for its nebulae, the great cathedrals of the Milky Way. We see the Lagoon Nebula, a sprawling cloud of glowing gas and dark dust lanes that spans dozens of light years. Within its depths, we see the Hourglass Nebula, a region where intense stellar winds have carved out a cavity in the gas, creating a shape that looks like a giant eye watching the cosmos. As we drift through the glowing pink hydrogen of the lagoon, feel the warmth of the radiation against your skin. This gas is being excited by the ultraviolet light of newborn stars, causing it to glow like a neon sign. It is a place of immense creation. We can see Bach globules, small, dense, black knots of dust that are currently collapsing to form new suns. They look like teardrops of shadow against the brilliant pink background. Everywhere we look, the galaxy is recycling. The atoms of old, dead stars are being gathered up and turned into new ones. This is the chemical evolution of the Milky Way. With every generation of stars, the galaxy becomes richer, more oxygen for water, more carbon for life, more iron for the cores of rocky planets. We are living in a mature galaxy, one that has spent 13 billion years preparing the ingredients for us. As you settle deeper into your pillows, imagine the Sagittarius Arm as a great, glowing wing wrapping around the center of the galaxy. We are moving faster now, drawn in by the increasing gravity of the bulge. The stars are changing color again, becoming more orange and yellow as we encounter older populations. We are now crossing the inner boundary of the Sagittarius Arm, entering the vast, glowing territory of the galactic bulge. As you sink deeper into your bed, notice how the scenery of the cosmos begins to change. The brilliant, fiery blues of the spiral arms are fading, replaced by a warm, honey-colored light. This is the light of the elders. The bulge is a dense, three-dimensional hub of stars at the center of our galaxy. If the disk we traveled through was a flat, spinning record, the bulge is the raised, rounded center. But as we move closer, we see that it is not a simple sphere. The Milky Way is a barred spiral, meaning a massive, straight bar of stars cuts through the center, like a bridge made of light. Imagine this bar as a giant, slow-moving propeller. It rotates much more slowly than the stars around it, acting as a gravitational stirrer. It funnels gas and dust from the spiral arms inward toward the center, fueling the heart of the galaxy with fresh material. Feel the slow, heavy rhythm of this rotation in your chest. It is a deep, resonant hum, the sound of billions of tons of matter moving in perfect, mathematical harmony. As we drift toward the very center of this bar, a strange and beautiful geometry reveals itself. Astronomers recently discovered that our bulge has a peculiar peanut shape. When viewed from the side, it swells in the middle and narrows at the ends, resembling a giant, glowing hourglass or a peanut shell made of stars. This shape was sculpted over billions of years. As stars in the central bar orbit, their paths become unstable. They begin to buckle and puff upward, rising thousands of light years above and below the galactic plane before curving back down. It is an X-shaped structure, a cosmic signature of the galaxy's age and maturity. Think of the billions of individual orbits required to maintain this shape, each star a tiny point of light following a complex, looping path, yet together they create a form of perfect, symmetrical beauty. In this region, the stars are packed so tightly that the interstellar medium, the gas and dust, is nearly gone. It has all been used up or blown away by the intense radiation of so many suns. The air here is clear and dry, and the starlight is constant. If you lived on a planet here, there would be no true night. The sky would be filled with thousands of stars, as bright as the full moon, casting soft, overlapping shadows across the landscape. The stars here are different from the ones in our neighborhood. They are metal-rich, containing high amounts of heavy elements like iron, magnesium, and silicon. This is because they were born in a region where many generations of stars have already lived and died, each one enriching the gas with the products of its own nuclear fire. This is the treasure chest of the galaxy, a place where the ingredients for rocky planets and complex chemistry are most abundant. Yet, despite the density, there is a profound sense of order. The stars do not collide. They move in a grand, coordinated stream, held together by the massive gravitational pull of the core. Feel the weight of that gravity now. It is not a heavy, crushing weight, but a firm, supportive embrace. It is the force that defines our home. As we float through the peanut of the bulge, notice the globular clusters that we saw in the halo appearing again, but here they are different. They are being slowly dismantled by the intense tidal forces of the center. Their stars are being scattered, added to the general glow of the bulge. The galaxy is a master of integration, taking these ancient, tight-knit families and weaving them into the larger tapestry of the core. We are now standing at the very doorstep of the galactic center. The light here is blinding, filtered through a few remaining lanes of thick, black dust that swirl around the nucleus. Beyond this dust lies the final destination of our journey, the place where physics reaches its limit. But for now, stay here in the golden light of the bulge. Let the warmth of these ancient suns settle over you. Your mind is a quiet hall, and your body is a still lake. We have moved from the lonely halo, through the vibrant arms, and into the majestic heart of the Milky Way. The peanut-shaped bulge turns slowly around us, a monument to the power of gravity and the passage of time. You are a part of this architecture. You are a small, quiet witness to a structure that has stood for 13 billion years. We are now crossing the final threshold. As you breathe out, feel the density of the universe press in around you in a supportive, warm embrace. We have entered the nuclear star cluster, the densest collection of stars in the entire Milky Way. In the neighborhood of our sun, stars are separated by light years of empty space. But here, in the innermost few light years of the galaxy, there are millions of stars packed together like grains of salt in a jar. The light here is a shimmering, iridescent fog of white, blue, and gold. Because the stars are so close, their gravity constantly tugs on one another, creating a chaotic but beautiful swarm. Imagine millions of fireflies trapped in a glass sphere, each one a sun, each one moving in a fast, tight loop. This is the heart of the machine, the central engine that anchors everything we have seen so far. As we drift deeper into this cluster, we see a group of stars known as the S-stars. These are young, massive stars that move with a speed that is almost impossible to comprehend. They are traveling at millions of miles per hour, whipping around an invisible point in space. Watch them for a moment in your mind's eye. They are performing the fastest dance in the galaxy, tracing perfect, tight ellipses around a void. In the very center of that void lies Sagittarius A*, pronounced Sagittarius A star. It is the supermassive black hole at the heart of our home. It contains the mass of 4 million suns, yet it is smaller than the orbit of the planet Mercury. It is a point of no return, a place where the fabric of space and time is curved so sharply that not even light can escape its grasp. But do not feel fear. From our perspective tonight, Sagittarius A* is a silent conductor. It is currently in a state of rest, a sleeping giant. It is not a vacuum cleaner sucking in the galaxy. It is a gravitational anchor, the steady weight at the center of the spinning wheel. Most of the time, it sits in the dark, invisible and quiet. Occasionally, a cloud of gas or a stray asteroid wanders too close. As the material falls toward the event horizon, it is accelerated to nearly the speed of light. It heats up to millions of degrees, letting out a final, brilliant flare of X-rays before it vanishes forever. This is the heartbeat of the center, a flickering light in the darkest place in the universe. Think of the stillness at the very edge of the black hole. This is the event horizon. Beyond this line, the future and the past become one. It is the ultimate mystery, a place where our math fails and only wonder remains. But even here, we are connected to it. The entire Milky Way, the spiral arms, the nebulae, the sun, and your very life is tied to this central point by the invisible threads of gravity. We are now standing at the absolute center of our world. Look back the way we came. Look through the nuclear cluster, past the peanut bulge, through the Sagittarius and Perseus arms, all the way out to the lonely halo. You have traveled the full length of a 13-billion-year-old masterpiece. Feel the deep, low frequency of the center. It is a vibration that resonates through every atom in your body. You are grounded. You are centered. The world is turning, the galaxy is spinning, and you are resting at the very point of balance. As we leave the intense, crowded neighborhood of the nuclear star cluster, imagine yourself floating upward, perpendicular to the galactic disk. As the light of the millions of central stars begins to soften and merge into a single golden glow, the perspective shifts. You are no longer looking through the galaxy, you are looking at it from above. High above the galactic center, two ghostly, ethereal structures begin to emerge from the darkness. These are the Fermi bubbles. Discovered only recently by eyes that can see in gamma rays, these massive lobes stretch for 25,000 light-years above and below the disk. They are like giant, translucent balloons filled with high-energy particles and magnetic fields, glowing in a spectrum far beyond what human eyes can perceive. As you drift within the edge of one of these bubbles, feel the vast, quiet energy surrounding you. These structures are the breath of the galaxy, the remnants of a gargantuan outburst from the central black hole that occurred millions of years ago. Perhaps a massive cloud of gas fell into Sagittarius A*, causing it to flare with a brilliance that lit up the entire core. Or perhaps a sudden burst of star formation sent a super wind of hot gas screaming out of the disk. These bubbles are the echoes of that ancient violence, now cooled into a steady, silent radiance. Notice how the galaxy interacts with the space around it. The Milky Way is not a closed system. It is constantly exchanging matter with the intergalactic medium. Hot gas is blown out of the disk by supernova explosions, rising like steam into the halo, where it cools and eventually rains back down to form new generations of stars. This is the galactic fountain, a slow, majestic cycle of recycling that keeps the galaxy alive and evolving. In this high, thin atmosphere, we also encounter the high-velocity clouds. These are massive reservoirs of hydrogen gas, drifting far above the disk like cosmic rain clouds. Some are being drawn in for the first time from the spaces between galaxies, while others are returning from their journey in the fountain. They are the raw fuel for the future, the material that will eventually settle into the spiral arms to ignite the suns of billions of years from now. Look toward the horizon of the halo, and you will see a long, thin ribbon of gas stretching across the sky. This is the Magellanic Stream, a bridge of hydrogen pulled from our neighbor galaxies, the large and small Magellanic Clouds. It is a reminder that the Milky Way is a dominant force in its local neighborhood, a gravitational shepherd that influences everything around it. As you drift in this high, quiet place, let the scale of these structures settle your mind. You are witnessing a metabolic process on a galactic scale. The birth of stars, the death of giants, the flare of black holes, and the raining of gas. It is all part of a single, unified system that has been functioning for eons. Feel the stillness of the deep halo once again. Your breath is a slow, rhythmic tide. Your body is heavy and relaxed. You have seen the galaxy's heart, its arms, and now its very breath. The Milky Way is a living structure, and you are a tiny, cherished spark within its vast, enduring frame. As the image of the great Fermi bubbles fades into the soft dark, let your thoughts dissolve. You are suspended in the safe, quiet reaches of the cosmos. The galaxy is breathing. The stars are waiting. You are exactly where you need to be. As we descend from the towering gamma-ray lobes, the Milky Way begins to flatten out beneath us once again. Imagine the scale of this descent. We are dropping through thousands of light-years of empty space, watching the spiral arms sharpen from a fuzzy glow into intricate, winding rivers of light. But we are not aiming for the crowded, frantic center, nor the lonely, dark edges. We are aiming for the middle ground, the galactic habitable zone. In the vast architecture of the galaxy, Not every location is equal. There is a specific ring, a Goldilocks band that circles the center, where the conditions for life are just right. As you breathe in the stillness of your room, imagine this band as a celestial garden. If we were to go too far toward the center, the environment would become hostile. The radiation from the dense crowds of stars and the violent activity around the central black hole would scour the surfaces of planets, making life a fleeting, impossible dream. The gravitational tugs of so many neighbors would send comets screaming into worlds, bringing chaos instead of peace. But if we were to drift too far out, toward the very rim of the galaxy, the chemistry would fail us. In those sparse, lonely reaches, the stars are made of the most primitive materials, mostly hydrogen and helium. There aren't enough metals, the heavy elements like iron, silicon, and magnesium, to build a rocky Earth. Out there, the universe is a place of gas giants and frozen moons, lacking the solid ground required for a heartbeat to begin. We find ourselves now settling into that perfect middle path, about 26,000 light-years from the center. This is our home. It is a region of the Milky Way where the star formation rate is balanced. It is quiet enough for planets to form and remain stable for billions of years, yet rich enough in heavy elements that the dust can clump together into mountains, valleys, and oceans. As we float through this galactic garden, notice the Orion Spur rising up to meet us. This is the specific local arm where our sun resides. It is a gentle, minor bridge of stars tucked between two of the great, heavy spiral arms, the Sagittarius and Perseus arms. Think of it as a quiet, tree-lined street located safely between two roaring highways. Because we live in this spur, we are protected from the most intense star-forming regions that might otherwise threaten our world with the radiation of nearby supernovae. The Sun, our own star, is a yellow dwarf, a stable and patient source of energy. It has lived for 4.5 billion years, and it has only completed about 20 orbits around the galaxy since it was born. Imagine the Sun as a slow, steady traveler. It doesn't race through the galaxy. It drifts with a majestic momentum, carrying its family of planets along for the ride. Think about the timing of our lives. It has taken nearly 4 billion years for life on Earth to reach this moment, to reach the point where it can look up and understand the galaxy that contains it. For that entire time, the Milky Way has provided a stable environment. It has shielded us. It has fed us with the heavy elements created in ancient, dying stars. Feel the profound stability of your position in the universe. You are not on a world that is being tossed about by cosmic storms. You are in a safe harbor, a fine-tuned region of space that was billions of years in the making. The atoms of your body, the carbon in your DNA, the iron in your blood, were gathered from this specific part of the galaxy, recycled through generations of stars until the conditions were perfect for you to exist. As you settle into the deepest part of your rest, let the concept of the galactic habitable zone bring you a sense of belonging. You are not an accident. You are a product of a very specific, beautiful, and rare alignment of cosmic forces. The galaxy is a vast and often violent place, but it has carved out this quiet, golden ring just for life to flourish. The starlight of the Orion Spur is soft and constant. The rotation of our arm is steady and predictable. You are a passenger on a world that is perfectly placed, perfectly timed, and perfectly held. As we drift away from the comfort of the Orion Spur, imagine the stars beneath us beginning to merge into a single, glowing disk of milk and fire. We are rising so high now that the entire Milky Way, 100,000 light-years across, begins to look like a small, shimmering coin in a vast, dark ocean. The silence here is absolute, the kind of silence that has existed since the dawn of time. In this deep, intergalactic void, we realize we are not alone. Our galaxy belongs to a collection of about 80 members known as the local group. Most are small, humble dwarf galaxies, scattered like breadcrumbs across the dark. But there is one other titan in our midst. Look toward the constellation of Andromeda. There, 2.5 million light-years away, glows a mirror of our own home, the Andromeda Galaxy, or M31. It is a spectacular spiral, slightly larger than ours, containing nearly 1 trillion stars. For billions of years, we have been falling toward each other. Gravity, that invisible and tireless thread, is drawing us together at a staggering speed of 250,000 miles per hour. As you breathe, feel the slow, steady pull of that distant giant. It is not a violent force, but a patient, inevitable destiny. Even though we are moving toward each other so quickly, the distance is so vast that it will take another 4 to 5 billion years for us to finally meet. Imagine the night sky of the distant future. As eons pass, Andromeda will grow larger and larger in our sky. It will no longer be a faint smudge of light, but a magnificent, glowing bridge that stretches from one horizon to the other. Two rivers of stars, two spiraling hearts, approaching each other in a dance that has been choreographed since the beginning of the universe. When the collision finally begins, it will be the most beautiful event in the history of our world. But collision is a misleading word. Galaxies are mostly empty space. If the sun were a ping-pong ball in New York, the nearest star would be a pea in Chicago. When the Milky Way and Andromeda pass through one another, the individual stars will almost never touch. Instead, they will glide past each other like ghosts, their paths curved and redirected by the shifting gravity of the two giants. The real magic happens to the gas. As the great clouds of hydrogen from both galaxies slam into each other, they will be compressed into a fever of creation. Thousands of new, brilliant blue stars will ignite at once, illuminating the merger with the light of a million supernovae. The spiral arms will be torn apart, stretched into long, delicate tidal tails of stars that reach out into the void for hundreds of thousands of light years. Eventually, after a series of slow, graceful passes, the two will settle. They will lose their spiral shapes and merge into a single, massive, golden sphere, a giant elliptical galaxy that astronomers have already named Milky Way. Think about our sun in this future. There is a 50% chance that our solar system will be flung out into the far reaches of the new galaxy, 3 times further from the center than we are now. There is even a small chance we could be ejected into the intergalactic void entirely, becoming rogue travelers in the dark. But even then, we would be safe. We only need our sun to survive, and the sun will continue to shine, indifferent to the shifting geometry of the stars around it. As we drift further into the intergalactic void, the Milky Way and Andromeda begin to shrink, becoming just 2 tiny sparks of light amongst thousands of others. We are rising into the highest vantage point possible, where the individual galaxies no longer look like islands, but like droplets of water flowing through a vast, invisible river system. Imagine the universe not as empty space, but as a cosmic web. This is a delicate, glowing network of filaments, long threads of dark matter and gas that stretch across billions of light years. Galaxies cling to these threads like morning dew on a spider's web. Where the threads cross, huge concentrations of galaxies form. These are the superclusters, and we are currently entering our own Laniakea. The word Laniakea comes from the Hawaiian language, meaning immense heaven or open skies. It is a fitting name. This structure is over 500 million light-years across. It contains more than 100,000 galaxies, each one a home to billions of stars. As you breathe in the stillness of your room, try to visualize this scale. If the Milky Way were a single grain of sand, Laniakea would be an entire beach. As we drift through this immense heaven, notice that the galaxies aren't just sitting still. They are moving. They are following flow lines, drifting toward a common destination. In Laniakea, every galaxy, including our own Milky Way, is being drawn toward a central gravitational focal point known as the Great Attractor. The Great Attractor is one of the most mysterious regions in the cosmos. It lies in the direction of the constellations Centaurus and Norma, but we cannot see it clearly. It is hidden behind the zone of avoidance, the thick, dusty plain of our own Milky Way that acts like a curtain, blocking our view of the deep universe. But even though we cannot see it, we can feel it. Imagine a vast, invisible valley in the fabric of space. All the galaxies in Laniakea are like sleds sliding down the sides of this valley, gathering speed as they head toward the bottom. Our Milky Way is currently screaming toward this point at over 1 million miles per hour. Yet, Because the distances are so unfathomably large, we will never arrive. The expansion of the universe is pushing galaxies apart even as gravity tries to pull them together. It is a cosmic tug of war, a balance of forces that keeps the universe in a state of eternal, rhythmic tension. Look around you at the spaces between the filaments. These are the voids. They are the loneliest places in existence, vast bubbles of nothingness that can be hundreds of millions of light years wide. Within these voids, there are almost no stars, no planets, and no light. They are the great silences of the universe. Being in Laniakea is like being part of a great celestial family. We are tied to these 100,000 other galaxies by the invisible bonds of gravity. We are part of a structure so large that light takes 500 million years just to cross it. And yet, even Laniakea is just a small branch on an even larger tree. Beyond us lie even greater concentrations of mass, like the Shapley supercluster, toward which our entire immense heaven is slowly drifting. We have risen so high that even the superclusters have vanished into a faint, distant haze. The universe is stretching out before us, but we are no longer traveling through space alone. We are traveling through time. As you settle into the deepest parts of your rest, imagine the clock of the cosmos winding backward. The galaxies grow closer together. The voids shrink. The temperature of the dark begins to rise. We reach a point approximately 13.8 billion years in the past. Here, the universe is a thick, opaque fog of hot, glowing plasma, a primordial soup of protons and electrons. It is so dense that light cannot travel. Every photon is immediately scattered by a charged particle. The universe is a brilliant, white-hot wall of fire. But then, a moment of profound peace occurs. It is called recombination. The universe has cooled just enough, to about 3,000 degrees Celsius, for electrons to settle into orbits around protons, forming the first neutral atoms of hydrogen. Suddenly, the fog clears. The light that was trapped for 380,000 years is suddenly set free. It streams across the cosmos in every direction at once. This is the cosmic microwave background, CMB. It is the fossil light of the Big Bang. Over the eons, the expansion of the universe has stretched these ancient light waves, cooling them until they are no longer visible light, but faint microwaves. Even as you lie in your bed, this radiation is all around you. It is a subtle wallpaper that fills every corner of the sky, a quiet whisper from the moment the universe first became transparent. In the CMB, we see tiny ripples, fluctuations in temperature of just a fraction of a degree. These were the seeds of everything we have seen on our journey. The areas that were slightly denser drew in more gas through gravity, eventually becoming the Laniakea supercluster, the Milky Way, our sun, and finally, the atoms that make up your very existence. You are literally a ripple in the first light of time. But now we must turn our gaze forward. We must look at where this great story is heading. As we watch the universe continue to expand, we see three possible futures. The first, and most likely according to our current understanding, is the Big Freeze or heat death. In this scenario, the universe continues to expand forever. The galaxies drift so far apart that they can no longer see each other. One by one, the stars exhaust their fuel. The blue giants go first, then the yellow suns like ours, and finally the tiny red dwarfs. The universe grows dark. The black holes eventually evaporate through Hawking radiation, leaving nothing but a thin, cold mist of particles. The universe reaches a state of maximum entropy, a perfect, eternal equilibrium. It is the ultimate rest. The second possibility is the Big Crunch. In this version of the story, the expansion eventually slows and reverses. Gravity wins the tug of war. The galaxies begin to rush back toward each other. The night sky grows brighter and hotter as the universe contracts. Eventually, everything we have seen, the stars, the planets, the superclusters, is crushed back into a single, infinitesimally small hot point. A singularity. Perhaps, from that point, another Big Bang occurs, and the story begins all over again in a great cycle. The third is the Big Rip. Driven by the mysterious force of dark energy, the expansion of the universe accelerates so fast that gravity can no longer hold things together. First, the superclusters are torn apart, then the galaxies, then the stars and planets. Finally, even the atoms themselves are ripped asunder by the stretching of space-time itself. We have traveled to the very beginning of time and the very edge of the cosmic web. But now, the great pull of home begins to guide us back. Imagine the light of distant superclusters fading into the background, becoming a soft, static hum. We are zooming back in, through the Laniakea filaments, past the Andromeda Galaxy, and into the silver-blue glow of the Milky Way's Orion Spur. We are back in our local neighborhood, but we aren't stopping at the sun. We are going to visit the family of worlds that share our small corner of the dark. These are the planets, the silent sentinels that have kept us company for 4.5 billion years. As you settle deeper into your rest, feel the familiarity of this place. This is your solar system. This is your home. Our first stop is a world of iron and echoes, Mars. As we drift toward the red planet, the first thing you notice is the color. Not a fiery red, but a soft butterscotch orange, the color of dried apricot and ancient rust. Mars is a desert world, a place where the wind has been whispering across the rocks for billions of years. There are no oceans here, no forests, no cities. There is only the vast, quiet dignity of the geological past. Imagine standing at the edge of Valles Marineris, the Grand Canyon of Mars. It is so large that if it were on Earth, it would stretch from New York to Los Angeles. From your vantage point, the opposite rim is so far away that it disappears over the horizon. The canyon walls are thousands of feet deep, showing layers of rock that were laid down when Mars was young, when water may have flowed through these very valleys. Feel the absolute stillness of the Martian air. It is thin and cold, composed mostly of carbon dioxide. On a quiet afternoon, a dust devil might dance across the floor of the canyon, a tiny, swirling ghost of a storm that leaves a dark trail in the red sand. This is a world that has retired. It is a planet in a long, peaceful sleep, holding the secrets of a time when it might have been a twin to the Earth. Further to the west, we see Olympus Mons, the largest volcano in the solar system. It is a shield volcano, so wide and so tall that it pokes through the top of the atmosphere and out into the black of space. Standing on its summit, you wouldn't feel like you were on a mountain. The slope is so gentle that you would feel as though you were standing on a vast, endless plain of basalt. Mars reminds us of the fragility of life and the beauty of persistence. It is a world of what-ifs, a silent witness to the early days of our sun. As we drift away from its orange sands, let the stillness of Mars settle your mind. The red desert is quiet. The dust has settled. Getty images. We move now across the asteroid belt. This is not the crowded, dangerous field of rocks you see in movies. In reality, the asteroids are millions of miles apart. It is a region of immense space, filled with space potatoes, chunks of rock and ice that never quite made it into a planet. Among them is Ceres, a dwarf world that is part rock and part ice. It has mysterious bright spots on its surface, salt deposits left behind by water that seeped up from an underground ocean long ago. Ceres is a bridge between the inner rocky worlds and the outer giants. It is a quiet, lonely place, a remnant of the building blocks that created our world. Now, the light of the sun begins to dim as we enter the realm of the giants. We are approaching Jupiter, the king of planets. Jupiter is not a solid place. It is an immense ball of hydrogen and helium, a planet of storms and shadows. As we drift toward its atmosphere, we see the Great Red Spot, a hurricane 3 times the size of the Earth that has been raging for at least 400 years. It is a swirl of crimson and brick red, a beautiful, violent heart at the center of the giant. But beneath the storms, there is a different kind of majesty. Jupiter's gravity is so strong that deep inside, the hydrogen gas is crushed into a liquid metal. This metal creates a magnetic field so vast that it reaches all the way to Saturn. Jupiter is the protector of the solar system. Its gravity acts like a cosmic vacuum cleaner, sucking in comets and asteroids that might otherwise head toward Earth. Feel the immense power of Jupiter. It is a steady, rhythmic presence, a heavy anchor in the outer solar system. Around it dance dozens of moons, each one a world of its own. We pause at Europa. This is a world of ice, white and smooth, crisscrossed by long, reddish cracks. Beneath that ice lies a global ocean of liquid water, more water than all the oceans of Earth combined. Imagine the dark, silent depths of that ocean, kept warm by the gravitational kneading of Jupiter. In that darkness, life might be swimming right now, untouched by the light of the sun. It is a world of hidden potential, a secret garden buried under miles of frozen crust. The chemical recycling of the Milky Way is a slow and sacred process that has been occurring for nearly 13 billion years. Every time a massive star reaches the end of its life and collapses, it creates a pressure so intense that it fuses simple atoms into complex ones. When that star explodes, it acts as a cosmic sower, scattering these newly minted elements across the vast, cold plains of the interstellar medium. This enriched gas then lingers in the dark, cooling and condensing over millions of years until it becomes the seed for a new generation of stars. We are the direct beneficiaries of this ancient agriculture. The very carbon in your DNA was once part of a different star, in a different part of the galaxy billions of years before our sun was even a spark in the dark. Consider the sheer volume of the dark nebula clouds, such as the Coal Sack or the Great Rift, that we see silhouetted against the bright band of the Milky Way. These are not empty holes in space, but incredibly dense reservoirs of cold molecular hydrogen and microscopic dust. Inside these shadowed cathedrals, the temperature drops to just a few degrees above absolute zero. In this profound cold, gravity works with a quiet, unrelenting patience, drawing together the dust into protoplanetary disks. These disks are the birthplaces of worlds. As you lie in the stillness of your room, imagine trillions of these tiny, spinning saucers of dust scattered throughout the spiral arms, each one a potential future Earth, each one waiting for its moment to ignite and begin the long journey toward life. The movement of our solar system through the galaxy is not a straight line, but a complex, three-dimensional dance. As we orbit the galactic center, we are also oscillating vertically, bobbing up and down through the dense midplane of the disk like a needle through fabric. Every 30 million years or so, we pass through the most crowded part of the galaxy, where the gravitational influence of nearby stars and gas clouds is at its peak. This rhythmic motion connects us to the larger pulse of the Milky Way. We are currently moving upward, rising into a clearer, thinner region of space, giving us a front-row seat to the deep cosmos. This galactic seasonality is so slow that it transcends human history, yet it is as regular and predictable as the changing of the leaves on Earth. Beyond the stars we can see, the Milky Way is enveloped in a hot gaseous halo that glows in X-rays. This halo is an immense reservoir of million-degree gas that extends hundreds of thousands of light-years into the void. It acts as a thermal blanket, regulating the temperature of the galaxy and providing a buffer against the intergalactic winds. This gas is the exhaust of billions of years of star formation, a ghostly atmosphere that contains as much mass as all the stars in the galaxy combined. We are living inside a giant, warm bubble of plasma, a protective cocoon that separates our home from the freezing, empty stretches of the intergalactic medium. The magnetic web of the galaxy is another invisible layer of protection and order. Vast magnetic field lines, twisted by the rotation of the spiral arms, act as guide rails for cosmic rays, high-speed particles that would otherwise strip away the atmospheres of planets. These fields are anchored in the cold gas clouds and stretch thin across the voids, creating a shimmering, invisible architecture that mirrors the visible spiral. When you feel the weight of your body settling into sleep, imagine these magnetic lines of force threading through the air around you, silently shielding our world from the high-energy storms of the deep universe. It is a system of profound balance, where the smallest particle is influenced by the largest structures in existence. In the far reaches of the outer rim, where the stars are few and the light is dim, the Milky Way's disk begins to fray and flare. This is the galactic warp, a gentle curve in the edges of the galaxy caused by the gravitational tug of our neighbor galaxies, the Magellanic Clouds. Like a vinyl record left in the sun, the edges of our home are turned upward on one side and downward on the other. This subtle warping is a reminder that we are part of a local ecosystem, a family of galaxies that are constantly communicating through the language of gravity. Even the furthest star in our galaxy is not isolated. It is connected to the movement of the entire local group, a small part of a larger, harmonious whole. Within these nebulae, we also find Herbig-Haro objects, which are among the most fleeting sights in the galaxy. These are narrow jets of partially ionized gas ejected by newborn stars. They shoot out from the poles of a developing star at hundreds of miles per second, colliding with the surrounding dust and creating glowing knots that last only a few thousand years. They are the birth cries of a sun, a visual representation of the immense energy required to begin the process of nuclear fusion. They remind us that the birth of a star is not a quiet event, but a powerful eruption of energy that clears the way for the stability that follows. Within these nebulae, we also find Herbig-Haro objects, which are among the most fleeting sights in the galaxy. These are narrow jets of partially ionized gas ejected by newborn stars. They shoot out from the poles of a developing star at hundreds of miles per second, colliding with the surrounding dust and creating glowing knots that last only a few thousand years. They are the birth cries of a sun, a visual representation of the immense energy required to begin the process of nuclear fusion. They remind us that the birth of a star is not a quiet event, but a powerful eruption of energy that clears the way for the stability that follows. Eventually, these nebulae are dispersed by supernova remnants. When a massive star dies, it releases a shockwave that travels outward at a significant fraction of the speed of light. This wave carries the heavy elements forged in the star's core, gold, silver, and uranium, and slams them back into the interstellar medium. The most famous of these, the Crab Nebula, still pulses with the energy of an explosion recorded by ancient astronomers nearly 1,000 years ago. These remnants are the enrichment centers of the galaxy, ensuring that every new generation of stars is chemically more complex than the last. We are the inheritors of 1 trillion such explosions. In the extreme corners of our galaxy, we find the magnetars, which are the most magnetic objects in the known universe. These are a rare type of neutron star with a magnetic field so intense that it defies the normal laws of matter. If a magnetar were located halfway to the moon, it would instantly wipe the data from every credit card on Earth and pull the iron from your very blood. This magnetic intensity is so great that it actually warps the shape of atoms, stretching them into long, thin cylinders. As you lie in the gentle gravity of your room, consider the power of these silent, spinning magnets, tucked safely away in the distant reaches of the spiral, acting as the extreme limit of what physics can endure. Traveling at even higher speeds are the hypervelocity stars, the outcasts of the Milky Way. These stars are moving so fast, millions of miles per hour, that they are not bound by the galaxy's gravity. Most were born in the crowded center of the galaxy as part of a binary pair. Then there are the pulsars, the cosmic lighthouses of the deep. A pulsar is a rapidly rotating neutron star that emits a beam of electromagnetic radiation from its poles. Because they spin with incredible precision, some hundreds of times per second, we perceive them as a rhythmic, ticking light. These stars are so stable that they can be used as galactic clocks, more accurate than the finest atomic clocks on Earth. In fact, the Pioneer plaque, sent out on the Voyager spacecraft, uses the positions of 14 pulsars to show any extraterrestrial intelligence exactly where our sun is located in the galaxy. We are mapped by the rhythm of these spinning ghosts. In the densest clusters, we find blue stragglers, stars that seem to defy the aging process of the universe. In a cluster where all stars were born at the same time, the massive blue ones should have died out billions of years ago. Yet, these stragglers remain, burning bright and blue. They achieve this stolen youth through a process of stellar cannibalism, colliding with or siphoning the gas from a neighbor star to rejuvenate their own nuclear fuel. They are the vampires of the star clusters, a reminder that in the crowded heart of the galaxy, the life of a star can be extended through the most dramatic and unexpected encounters. We must also consider the brown dwarfs, the stars that never truly woke up, often called failed stars. These objects are more massive than Jupiter, but not massive enough to ignite the hydrogen fusion that powers a true sun. They glow faintly in the infrared, slowly cooling over billions of years. Some even have weather, with clouds of molten iron rain and silicate dust. There may be as many brown dwarfs in the Milky Way as there are bright stars, hidden in the shadows of the spiral arms. They represent the quiet, middle ground of the universe, neither planet nor star, drifting in a perpetual warm twilight. High above the disk, we encounter the runaway stars, massive suns that have been kicked out of their birthplaces by supernova explosions. When a companion star explodes, the surviving star is suddenly released from its orbit, hurtling through space at hundreds of kilometers per second. As they plow through the thin gas of the halo, they create spectacular bow shocks, glowing arcs of compressed material that look like the wake of a celestial ship. They are the nomads of the galaxy, born in the heat of the disk but destined to die in the cold reaches of the halo, far from the nebulae that gave them life. Finally, there are the binary black holes, pairs of dark remnants that are slowly spiraling toward each other. As they orbit, they lose energy in the form of gravitational waves, tiny ripples in the fabric of space-time itself. Eventually, they will merge in a colossal event that sends a shudder through the entire galaxy. This process is the ultimate expression of the dance of gravity, a slow and inevitable union that transforms two dark hearts into one. As you reach the deepest level of your rest, imagine these waves passing through the room, a subtle, invisible vibration that connects every atom of your being to the furthest reaches of the Milky Way. The distant future of the Milky Way is a tale of cooling embers and the slow, inevitable triumph of gravity over light. Billions of years from now, after the merger with Andromeda has settled into the vast elliptical shape of Milkomeda, the galaxy will enter the degenerate era. During this epoch, the sprawling gas clouds that once birthed millions of suns will have been entirely exhausted. The vibrant pink nebulae will fade to black, and the sky will be populated only by the long-lived red dwarfs and the cooling husks of white dwarfs. This is the era of the red heavens, where the universe grows dimmer and colder, yet maintains a profound, quiet stability that lasts trillions of years, longer than the brief flash of the spiral era we live in today. As the last of the red dwarfs eventually exhaust their hydrogen, they will not explode, but quietly shrink into white dwarfs, joining the billions of others in the galactic graveyard. Over unimaginable timescales, roughly $10 $15 years, the orbits of these dead stars will decay. Through the process of dynamical relaxation, some stars will be flung out into the intergalactic void, while the rest will spiral inward toward the central supermassive black hole. The galaxy as a structural entity will begin to dissolve, its components either becoming lonely wanderers in the dark or being consumed by the growing shadows at the core. If protons are stable and do not decay, the universe enters the era of the iron stars. In this nearly eternal future, quantum tunneling allows the atoms within cold, dead white dwarfs to slowly transmute into iron, the most stable nuclear form. Over a period of $10 $1,500 years, these objects become pure spheres of cold iron, drifting in an absolute vacuum. These iron stars are the ultimate fossils of the Milky Way, the final solid remnants of the atoms that once made up our oceans, our mountains, and our bodies. They are monuments to the permanence of matter in a universe that has otherwise grown cold and dark. Eventually, even the black holes themselves will succumb to the laws of thermodynamics. Through the process of Hawking radiation, these behemoths will slowly leak mass back into space in the form of subatomic particles. This process is incredibly slow for a supermassive black hole like the one at our center, taking perhaps $10 $100 years to complete. In their final moments, these black holes will vanish in a tiny, silent flash of gamma rays, leaving the universe filled with nothing but a thin, cooling mist of photons and leptons. The era of black holes will end, giving way to the dark era. In the dark era, the expansion of the universe has pushed all other galaxies beyond the horizon of visibility. The remnants of our Milky Way, the photons and electrons, are spread so thin that they rarely, if ever, encounter one another. The temperature of the cosmos approaches absolute zero. Time itself becomes meaningless, as there are no more events, no more light, and no more change. It is the ultimate expression of entropy, where energy is perfectly and evenly distributed across an infinite expanse. It is a state of absolute, unbreakable rest. Yet, even in this final silence, some theories suggest a Poincare recurrence. Given an infinite amount of time, the random fluctuations of particles in a vacuum could, by pure chance, rearrange themselves into the exact configuration of our galaxy once again. A new Big Bang could spark from the void, or a Boltzmann brain could flicker into existence for a fraction of a second, remembering the smell of rain or the glow of a sunset. It is a mathematical hint that the story of the Milky Way may be part of an infinite cycle, a breath in a much larger cosmic lung. As you drift now into the deepest possible sleep, let the vastness of these timescales soothe you. The trillions of years ahead are a testament to the endurance of the universe. The atoms you are made of are part of a masterpiece that is nowhere near its end. You are resting in the golden age of the cosmos, a time of light, warmth, and complexity. The stars are still burning, the Earth is still turning, and you are exactly where you are meant to be in the great timeline of existence. The journey is complete. The long history of the light has been told. The final silence of the iron stars is a peace that surpasses all understanding. Your breath is the only sound in the universe. The Oort cloud is the true edge of the sun's kingdom, a vast, spherical shell of icy debris that surrounds our solar system like a ghostly cocoon. It is located so far away, nearly a light year from the sun, that it takes the light of our star over 10 months to reach its innermost border. Within this cloud, trillions of cometary nuclei, ancient remnants from the dawn of the solar system, drift in a state of perpetual deep freeze. They are the dirty snowballs of the cosmos, composed of water ice, ammonia, methane, and dust that has remained untouched for 4.5 billion years. As you breathe, imagine the silence of this place, where the sun is just the brightest star in a sky of eternal winter. Occasionally, a passing star or the tidal pull of the Milky Way's disk gives one of these icy travelers a gentle gravitational nudge. This starts a journey that will take millions of years, as the comet begins to fall toward the inner solar system. As it approaches the sun, the warmth causes the ices to sublimate, turning directly into gas and creating the magnificent comet tails that stretch for millions of miles. These tails always point away from the sun, blown back by the invisible solar wind. A comet is a messenger from the deepest dark, a piece of the ancient Oort cloud brought into the light to remind us of the vast, frozen reservoirs that wait at the edge of our home. Between the stars of the Milky Way, we find the local interstellar cloud, or the fluff. This is a region of gas and dust about 30 light-years across that our solar system is currently drifting through. The density here is incredibly low, yet it is enough to interact with the sun's heliosphere, the protective bubble of magnetic fields and solar wind that surrounds our planets. The boundary where the solar wind meets the interstellar fluff is called the heliopause. This is the point where the sun's influence finally yields to the pressure of the galaxy. Our Voyager spacecraft have already crossed this threshold, becoming the first human objects to taste the true, raw environment of the interstellar void. In the spaces between the star systems of our local arm, there are rogue planets that have no sun to call their own. These worlds were likely ejected from their original solar systems during the chaotic period of planetary formation. Without a star to warm them, they are frozen solid, with atmospheres that have collapsed and turned into nitrogen snow on their surfaces. Yet, beneath miles of ice, some of these rogue worlds might harbor internal heat from radioactive decay, keeping oceans of liquid water warm for billions of years. They are the dark wanderers of the galaxy, floating through the interstellar medium in total, peaceful isolation, invisible to all but our most sensitive infrared telescopes. In the distant reaches of the observable universe, we find the quasars, the most luminous objects in existence. A quasar is the glowing heart of a young galaxy, powered by a supermassive black hole that is consuming matter at an incredible rate. As gas and stars spiral into the black hole, they form an accretion disk that heats up to millions of degrees, releasing more light than an entire galaxy of 100 billion stars combined. These beacons are so bright they can be seen from across the span of 13 billion light-years, acting as cosmic lighthouses that show us what the universe looked like when it was still in its infancy. Related to these are blazars, which occur when one of the powerful jets of high-energy particles shooting out from a supermassive black hole is pointed directly at Earth. These jets travel at nearly the speed of light, carrying magnetic fields and radiation that can fluctuate in brightness in just a few hours. When you consider a blazar, you are looking down the barrel of the universe's most powerful particle accelerator. This energy travels across the vast intergalactic voids, a beam of pure intensity crossing the dark, reminding us that the centers of galaxies are places of unimaginable power and transformation. The expansion of the universe itself is driven by the most mysterious force of all, dark energy. Unlike gravity, which pulls things together, dark energy acts as a repulsive force that pushes the fabric of space-time apart. It makes up roughly 68% of the total energy in the universe, yet we cannot see it, touch it, or measure it directly. We only know it exists because we see the galaxies at the edge of our vision moving away from us faster and faster every second. It is the empty space itself that is growing, creating more distance between the stars even as you sleep. In the early universe, before the first stars ever ignited, there was a period known as the cosmic dark ages. For hundreds of millions of years, the universe was filled only with a cold fog of hydrogen and helium gas. There was no light, no heat, and no stars. It was a time of absolute potential. Eventually, gravity pulled the first clouds of gas together to form population 3 stars, monstrous, pure suns that were hundreds of times more massive than our sun. These first stars ended the Dark Ages, bringing the first light to the cosmos and forging the very first heavy elements that would one day become the planets. We also find gravitational lenses, where the mass of a foreground galaxy cluster is so great that it actually bends the light from a more distant object behind it. This creates a cosmic magnifying glass, stretching the image of a distant galaxy into long, glowing arcs or even multiple copies of the same image. This phenomenon, predicted by Einstein, allows us to see objects that would otherwise be too faint or too far away to detect. It proves that space-time is not just an empty stage, but a flexible, physical fabric that can be warped and shaped by the presence of matter. Finally, there is the Great Attractor, a gravitational anomaly located in intergalactic space at the center of the Laniakea supercluster. It is a region of such immense mass that it is pulling the Milky Way and thousands of other galaxies toward it at a speed of over 600 kilometers per second. We cannot see exactly what it is because it is hidden by the zone of avoidance, the thick dust of our own galactic plane. However, its influence is undeniable. We are all on a grand, collective journey toward this invisible destination, a slow-motion migration across the supercluster that defines our place in the cosmic hierarchy. As your mind drifts further into the dark, let the scale of these mysteries provide a sense of profound perspective. The quasars are shining, the dark energy is pushing, and the gravitational lenses are bending the light of the past. The universe is a vast, dynamic, and complex machine, functioning with a precision that spans billions of light years. You are resting in a safe, quiet pocket of this machine, a conscious witness to the grandest story ever told. The life cycle of a star begins in the deepest, coldest reaches of a giant molecular cloud. These are the nurseries of the cosmos, where vast billows of hydrogen gas and microscopic silicates linger in the dark. A ripple of gravity, perhaps from a distant supernova or the passing of a spiral arm, disturbs the cloud, causing a pocket of gas to begin to collapse under its own weight. As the gas falls inward, it gains speed and heat, forming a protostar at its center. This infant sun is still shrouded in a thick cocoon of dust, invisible to the eye but glowing brightly in the infrared. It is a moment of pure potential, a gathering of mass that will soon challenge the darkness of space. Once the core of the protostar reaches a staggering temperature of 15 million degrees, a miracle of physics occurs. Nuclear fusion ignites. Hydrogen atoms are slammed together with such force that they fuse into helium, releasing a tremendous burst of energy. This outward pressure of light and heat perfectly balances the inward pull of gravity, reaching a state of hydrostatic equilibrium. The star is now a main sequence star, just like our sun. It will spend the majority of its life in this stable state, steadily converting its fuel into light, providing the warmth and energy that can eventually foster life on surrounding planets. As the star ages and its hydrogen fuel begins to run dry, its internal structure must transform to survive. For a star like our Sun, the core will shrink and heat up, while the outer layers expand and cool, turning the star into a red giant. During this phase, the star becomes hundreds of times larger than its original size, swallowing any inner planets in its path. The star then begins to fuse helium into heavier elements like carbon and oxygen. This is the stellar metamorphosis, a grand and beautiful expansion that marks the beginning of the end for the star's long journey. For more massive stars, those at least 8 times the size of our Sun, the end is much more violent. These giants do not stop at carbon. They continue to fuse heavier and heavier elements, creating layers like an onion. They forge neon, magnesium, silicon, and finally iron. However, fusing iron consumes energy rather than releasing it. In a fraction of a second, the outward pressure vanishes, and the star's core collapses. This results in a Type II supernova, a catastrophic explosion that outshines an entire galaxy. In this final, brilliant flash, the heaviest elements like gold, silver, and uranium are created and blasted into space. What remains after the explosion depends on the mass of the original star's core. If the core is between 1.5 and 3 times the mass of the Sun, it collapses into a neutron star. This is an object so dense that its atoms have been crushed together, turning the entire star into a sphere of pure neutrons. A neutron star just 12 miles across weighs more than our Sun. If the core is even more massive, gravity wins the final battle, and the core collapses infinitely into a stellar mass black hole. This is a point where the laws of physics as we know them cease to exist, and the star becomes a permanent shadow in the fabric of the universe. For smaller, more humble stars like red dwarfs, the life cycle is much longer and quieter. Because they burn their fuel so slowly, a red dwarf can live for trillions of years, longer than the current age of the universe. They never explode and never become red giants. Instead, they simply grow dimmer and cooler over eons, eventually fading into blue dwarfs and finally white dwarfs. These stars are the long-distance runners of the cosmos, the steady lanterns that will remain lit long after the more spectacular giants have vanished from the sky. High above and below the flat plane of the Milky Way, we find the globular clusters. These are massive, tightly packed spheres containing hundreds of thousands, sometimes millions of stars, all bound together by their mutual gravity. They orbit the galactic center in the halo, far from the dust and gas of the spiral arms. To look at a globular cluster through a telescope is to see a glittering swarm of bees frozen in time. These are the old guard of the galaxy, the most ancient structures in our local universe. The stars within these clusters are some of the oldest in existence, dating back over 13 billion years. They were born shortly after the Big Bang, during the cosmic dawn. Because they formed so early, they have very low metallicity, meaning they contain almost no elements heavier than hydrogen and helium. They are pristine fossils of the early universe. As you lie in your bed, imagine these ancient suns, having burned steadily for nearly the entire history of time, watching as the rest of the galaxy grew and changed around them. Because the stars in a globular cluster are so densely packed, the night sky on a planet inside one would be unlike anything we can imagine. In the center of a cluster like Omega Centauri, stars are only a few light weeks apart. Instead of a few thousand stars visible to the naked eye, the sky would be filled with tens of thousands of suns, as bright as the full moon. There would never be true darkness, only a perpetual, shimmering twilight. This crowded environment, however, makes the formation of stable planetary systems difficult. The gravitational tug of passing stars would likely strip away any planets that tried to form. Globular clusters are the keys to understanding the age of the universe. By studying the turn-off point of their stars, the moment they stop fusing hydrogen and begin to die, astronomers can calculate exactly how long the cluster has been in existence. For a long time, these clusters appeared to be older than the universe itself, a mystery that was only solved when we discovered the accelerating expansion of space. Today, they stand as the oldest markers on our cosmic map, the anchors that prevent our understanding of history from drifting away. As the Milky Way orbits through the local group, these clusters act as gravitational probes. As they plunge through the disk of our galaxy, they feel the pull of dark matter. By tracking their orbits, we can map the invisible halo of dark matter that surrounds us. Some of these clusters aren't even original to the Milky Way. They are the cores of former dwarf galaxies that our home cannibalized billions of years ago. They are the trophies of a long history of galactic growth, the survivors of a cosmic struggle for dominance. In the heart of some globular clusters, scientists suspect the presence of intermediate-mass black holes. These are the missing links between the small black holes created by single stars and the supermassive giants at the centers of galaxies. These hidden weights help hold the cluster together, keeping the hundreds of thousands of stars in their tight, spherical dance. Even in these ancient, stable relics, there is a dark, powerful heart driving the movement of the light. In the vast architecture of the cosmos, we move far beyond the crowded neighborhoods of clusters and filaments into the great cosmic voids. These are the most expansive, empty spaces in existence, colossal bubbles of nothingness that can span hundreds of millions of light years. While the Milky Way sits in a vibrant river of light, the voids are the deserts of the universe. To enter a void is to experience a silence so profound that it defines the very scale of the vacuum. As you lie in the quiet of your room, imagine the sheer luxury of this space, where there are no stars for millions of miles in every direction. Within these voids, we occasionally find void galaxies, the loneliest objects in the universe. These are typically small, gas-rich galaxies that have formed in total isolation, far from the gravitational tug-of-war of the cosmic web. Because they have no neighbors to collide with or steal their gas, they evolve in a state of pristine solitude. They are the hermits of the cosmos. A planet inside a void galaxy would have a night sky that is almost entirely black. Aside from the stars of its own galaxy, there would be no other smudges of light, no distant spirals, and no neighbor systems. There is only the one island of light in an infinite sea of shadow. The voids are not just empty space. They are the primary drivers of the universe's expansion. Because they contain so little matter, the dark energy within them is unopposed by gravity. This causes the voids to act like expanding balloons, pushing against the surrounding filaments of galaxies and stretching the cosmic web thinner and thinner. We used to think the walls of galaxies were the most important part of the universe, but we now know the voids make up over 90% of its volume. The universe is not a collection of things. It is a collection of vast, expanding silences. Despite their name, voids are not perfectly empty. They contain a very thin, hot gas known as the warm-hot intergalactic medium, WIM. This gas is so diffuse that there might only be one atom per cubic meter. However, because the voids are so enormous, this nothingness actually accounts for a huge portion of the missing baryonic matter in the universe. It is a ghost-like fog, invisible to the eye but detectable by the way it absorbs the light of distant quasars. You are breathing in a room full of air, but the universe is breathing through these vast, empty chambers of hydrogen. In the future, the voids will win. As dark energy continues to accelerate the expansion of space, the voids will grow larger and the filaments will snap. Eventually, every group of galaxies, including our own local group, will become its own island universe, surrounded by an infinite, impassable void. The light from other galaxies will be stretched so far that it will fade away entirely, leaving us in a state of ultimate cosmic isolation. But this is the peace of the far future, a time when the universe has finally finished its work and settled into a state of perfect, quiet equilibrium. The cosmic web is the largest coherent structure in existence, a vast, glowing scaffolding that spans the entire observable universe. It is composed of colossal filaments of dark matter and hydrogen gas that stretch across billions of light years, acting as the connective tissue of the cosmos. If you were to zoom out until galaxies became mere points of light, you would see that they are not scattered randomly, but are strung along these threads like glowing beads on a string. As you lie in the stillness of your room, imagine this invisible net holding every star and every galaxy in its place, a grand design that ensures no part of the universe is truly isolated. At the intersection of these great filaments lie the galaxy clusters, the most massive gravitationally bound objects in the universe. These are the nodes of the cosmic web, where hundreds or even thousands of galaxies are pulled together by the immense gravity of dark matter. Within these clusters, galaxies are in constant motion, dancing around a common center of mass and occasionally colliding to form even larger structures. This is the busiest part of the universe, a high-energy environment where the intergalactic gas is heated to millions of degrees, glowing with X-rays that reveal the hidden weight of the cluster. The primary ingredient of the cosmic web is dark matter, a mysterious substance that does not emit, absorb, or reflect light. We cannot see it, yet it makes up about 85% of all the matter in the universe. Dark matter provided the initial gravitational seeds that allowed the first atoms to clump together shortly after the Big Bang. Without this invisible framework, the gas of the early universe would have remained spread too thin to ever form stars or galaxies. You are resting today because, billions of years ago, dark matter pulled the universe into the shapes we see today, creating the stable foundations of the Milky Way. Connecting the nodes are the intergalactic filaments, long rivers of gas that act as the supply lines for the universe. Fresh hydrogen flows along these filaments, feeding into galaxies and providing the raw material for new generations of stars. These threads are incredibly thin and difficult to detect, but they are the lifelines of the cosmos. When we see a star being born in our own galaxy, we are seeing the end result of a journey that began millions of light years away, as gas traveled along the cosmic web to reach its destination. It is a system of profound and ancient circulation. The cosmic web is not a static structure. It is a living, evolving map of the universe's history. As dark energy pushes the voids apart, the filaments are being stretched and thinned. Over trillions of years, the web will eventually fray and break, leaving the galaxy clusters as isolated islands in an infinite sea of empty space. But for now, we live in the era of connectivity, a time when the universe is perfectly balanced between the pull of gravity and the push of expansion. Every atom in your body is a part of this web, connected to the furthest reaches of space by the invisible threads of physics. As we move beyond the grand scaffolding of the cosmic web, we arrive at the final frontier of our journey, the multiverse and the infinite horizon. This is the realm of pure theoretical majesty, where we contemplate the possibility that our entire universe, with all its galaxies, voids, and filaments, is just one bubble in an endless, frothing sea of other realities. In this final hour of thought, let the boundaries of the possible dissolve into a sense of infinite, peaceful potential. The theory of cosmic inflation suggests that in the first trillionth of a second after the Big Bang, space expanded faster than the speed of light. This process may not have stopped everywhere at once. In some regions, space might still be doubling in size every fraction of a second, creating new bubbles of spacetime. Each of these bubbles would be its own universe, perhaps with its own laws of physics, its own version of gravity, and its own unique arrangement of stars. As you lie in the quiet of your room, imagine that for every choice made or every star born, there is a universe where the story went differently. You are a part of a tapestry that is truly without end. Within this multiverse, there is a concept known as quantum branching. Every time a subatomic particle makes a choice to spin one way or another, the universe could theoretically split into two parallel paths. This means there could be an infinite number of yous resting in an infinite number of rooms, each one safe, each one part of a different version of history. This infinite repetition means that nothing is ever truly lost. Every possibility exists somewhere in the grand, shimmering many worlds landscape. Feel the weight of your own existence as a single precious thread in a weave that contains everything that ever could be. We must also consider the holographic principle, a mind-bending idea from string theory. It suggests that all the information contained within a volume of space, like our entire universe, can actually be described by the information on the boundary of that space. In this view, our three-dimensional reality might be a projection of a two-dimensional code written on the furthest edge of the cosmos. As you drift towards sleep, imagine the universe as a beautiful, high-definition projection, a light show of incredible complexity and depth, all emerging from a simple, elegant set of laws. Beyond the physical universes lies the mathematical multiverse, the idea that every mathematical structure that can exist does exist as a physical reality. In this realm, the laws of geometry and calculus are the only true creators. Our universe is simply one possible solution to a grand equation. There is a profound peace in this logic. It suggests that the universe is not a random accident, but a necessary expression of truth. The same math that lets you count your breaths is the math that builds the stars. Finally, we look toward the omega point, a theoretical future where the complexity and consciousness of the universe reach a state of total unity. In this vision, the expansion of the universe and the evolution of life eventually merge into a single, divine moment of understanding. It is the point of all return, where the silence of the beginning meets the wisdom of the end. You are a vital part of this evolution. By simply being a conscious observer, by wondering at the stars, you are the way the universe looks at itself and understands its own beauty. The Kerr metric describes the region around a rotating black hole. Unlike a stationary black hole, a rotating one drags the very fabric of space-time around with it, a phenomenon known as frame dragging. As you settle into your blankets, imagine the space around the black hole spinning like a whirlpool. In this region, called the ergosphere, it is physically impossible to stand still. Space itself is moving faster than the speed of light. Yet, from a distance, this chaotic motion creates a perfect, glowing ring of light, a photon sphere, where light is trapped in a circular orbit destined to travel around the black hole forever. In the empty stretches between galaxies, we find cosmic strings. These are hypothetical, one-dimensional cracks in the fabric of the universe, formed during the rapid cooling of the Big Bang. A cosmic string would be thinner than an atom but would carry the weight of entire mountain ranges in every centimeter of its length. These strings would stretch across the entire observable universe, vibrating with immense tension. If you were to pass behind one, the light from distant stars would be split in two, creating a perfect double image. They are the infinite wires of the cosmos, remnants of a time when the universe was still choosing its shape. Consider the Great Repeller, a massive void in the direction of the constellation Centaurus. While the Great Attractor pulls our galaxy toward it, the Great Repeller does the opposite. Deep within the hearts of the largest galaxies lie ultramassive black holes, giants that are tens of billions of times more massive than our Sun. These objects are so large that their event horizons could swallow our entire solar system several times over. They are the ultimate gravity anchors of the universe. Around them, the tidal disruption events occur, moments when a star wanders too close and is shredded into a long, glowing stream of gas, a process known as spaghettification. This light can be seen across the universe, a final, brilliant scream from a star that has met the ultimate end. Finally, we contemplate vacuum decay. Some physicists suggest that our universe might be in a false vacuum, a state that is stable but not the lowest possible energy state. If a bubble of a true vacuum were to form somewhere in the cosmos, it would expand at the speed of light, rewriting the laws of physics as it passed. Within this bubble, atoms might not hold together or gravity might work differently. However, because the universe is so vast, the likelihood of this happening near us is almost zero. It is a reminder that the stability we enjoy, the way your room feels solid and the air feels certain, is a rare and beautiful gift of the current cosmic era. The moon Io, orbiting Jupiter, is the most volcanic place in the solar system. Caught in a gravitational tug-of-war between Jupiter and the neighboring moons Europa and Ganymede, Io's interior is constantly being squeezed and stretched. This tidal heating generates so much internal friction that the moon's rock is perpetually molten. Giant plumes of sulfur and sulfur dioxide erupt hundreds of miles into the cold vacuum of space, coating the surface in vibrant yellows, oranges, and reds. As you lie still, imagine the raw, subterranean power of a world that is essentially a giant, liquid heart, pulsing with the energy of gravity itself. Moving outward to Europa, we find a world of striking contrast. Underneath a thick, crisscrossed crust of water ice lies a global ocean of liquid salt water, containing twice as much water as all of Earth's oceans combined. This ocean is kept warm by the same tidal forces that melt the interior of Io. Deep on the dark seafloor of Europa, Hydrothermal vents may be spewing nutrients into the water, creating an environment that could, at this very moment, be home to extraterrestrial life. Imagine the silence of that deep, dark ocean, shielded from the radiation of space by miles of ice, a hidden sanctuary of warmth in the freezing dark. Around Saturn, the moon Enceladus provides even more direct evidence of hidden water. Through cracks in its southern pole, known as tiger stripes, Enceladus sprays massive geysers of water vapor and ice grains directly into space. These plumes are so powerful that they actually create one of Saturn's rings, the E-ring. Recent analysis of these grains has revealed complex organic molecules, the building blocks of life. Imagine standing on the surface of this small, white moon, watching a curtain of ice crystals rise miles above your head, glowing in the pale light of Saturn's rings. Saturn's largest moon, Titan, is a world that feels hauntingly familiar yet utterly alien. It is the only moon in the solar system with a thick atmosphere, a dense, orange haze of nitrogen and methane. On its surface, the temperature is so low that water acts like solid rock, and liquid methane and ethane flow through riverbeds into vast, mirror-still lakes. Titan has a full hydrological cycle, but instead of water rain, it rains liquid natural gas. It is a world in deep freeze, preserving a chemistry similar to what Earth might have looked like before life began. Finally, we reach Triton, the largest moon of Neptune. Triton is a captured world, likely a refugee from the Kuiper belt that was snared by Neptune's gravity. It orbits in the opposite direction of the planet's rotation, a retrograde orbit that is slowly spiraling inward. Triton's surface is covered in cantaloupe terrain and active nitrogen geysers that erupt dark, dusty material into its thin atmosphere. It is one of the coldest objects in the solar system, yet it is alive with geological activity. It is a reminder that even at the very edge of our sun's warmth, the forces of nature are busy carving landscapes and moving matter. We now descend from the frozen reaches of the gas giants, traveling back across the void to our own home. We pierce the atmosphere and dive deep beneath the soil, entering the deep architecture of the Earth. Beneath the familiar landscapes of mountains and forests lies a hidden world of immense pressure, liquid metal, and ancient heat that has been cooling since the planet's violent birth. The journey begins just miles beneath your bed in the Earth's crust. This is a thin, brittle shell, comparable to the skin of an apple, that is broken into massive tectonic plates. These plates float upon a semi-liquid layer called the mantle. They move at the same speed your fingernails grow, constantly colliding to create mountain ranges or pulling apart to birth new oceans. As you lie still, imagine the slow, tectonic power beneath you, a silent movement of continents that has been reshaping the map of the world for 4 billion years. Beneath the crust lies the mantle, a vast, solid but plastic reservoir of silicate rock that makes up 84% of the Earth's volume. Here, heat from the core creates convection currents, massive, slow-moving loops of hot rock that rise toward the surface and cool, then sink back down. This is the engine of the planet. Imagine these gargantuan, slow-motion rivers of red-hot rock, churning with the weight of entire oceans above them. This internal heat is the reason our planet is alive and geologically active, rather than a cold, dead husk like the moon. Deep within the mantle, the pressure becomes so great that the very structure of minerals changes. At the core mantle boundary, we reach the outer core, a 1,400-mile thick layer of liquid iron and nickel. The temperatures here are as hot as the surface of the sun, reaching 6,000 degrees C. Because this liquid metal is constantly swirling and flowing, it creates a massive dynamo effect. This is the source of the Earth's magnetic field. This field reaches out from the center of the planet and into space, forming a protective shield that deflects the solar wind. You are resting inside a giant, planetary-scale magnet, protected by the liquid fire swirling 3,000 miles beneath your feet. At the very center of our world lies the inner core, a solid ball of iron and nickel about the size of the moon. Despite the incredible heat, the pressure at the center of the Earth is so immense, over 3 million times the pressure at sea level, that the metal cannot melt. It is squeezed into a solid, crystalline sphere. Recent studies suggest this inner core may even be a giant, single crystal of iron, aligned with the Earth's axis. It is the densest, most stable part of our world, a solid anchor at the heart of the storm. The heat at the core comes from two sources: the primordial heat left over from the Earth's formation and the radioactive decay of elements like uranium and thorium. The Earth is a giant thermal battery that is slowly, very slowly running down. This heat prevents the oceans from freezing and allows the atmosphere to remain thick and protective. Every mountain you have ever climbed and every valley you have ever seen is a result of this deep, internal energy.